Today I'm going to continue my previous lecture on Nesterov smoothing. Our goal is to build smooth approximations for a more complicated class of functions. We consider the function f defined on Rn by the following formula. F of x is the supremum of the inner product of ax and u minus 5 of u, where u runs in Rm. Here, A is an m by n matrix, and 5 from Rm to the standard real line is proper lower semi-continuous and convex. And we can observe from the definition that f of x is phi star of ax for all x in Rn. Here, phi star is the Van-Til conjugate of 5. In the previous lecture, we already considered a particular case of this class of function where I is the identity matrix. And in that case, f is just the Van-Til conjugate of a function 5. In today's lecture, we are going to consider this new class of function, and we will follow a very similar procedure to that considered in the previous lecture to build such smooth approximations. There are two important steps of Nesterov smoothing. In the first step, we are going to choose a proximity function for the function f. So a function d defined on Rm is called a proximity function for the function f if the following conditions are satisfied. First of all, d is proper, lower semi-continuous, and strongly convex with parameter sigma. The second condition says that the domain of 5 is a subset of the domain of d. It means that the domain of d has to be large enough to contain the domain of 5. The third condition says that d has to be non-negative on the domain of 5. It means that d of x is greater than or equal to 0 for all x in the domain of 5. And the final condition says that the supremum of dx on the domain of 5 has to be a real number. It means that this is a real number. Okay, and in the second step of Nesterov smoothing, we will build a family of smooth approximations for the function f as follows. Given any positive real number mu, define f mu of x by the supremum of the inner product of ax and u minus 5 of u minus mu times d of u, where u runs in Rm. And observe from the definition that this is just 5 plus mu d star of ax. So this is just the composition of the Van-Til conjugate of 5 plus mu d and the matrix A. Okay, and observe also from the definition that f of mu is obtained from the definition of the function f by subtracting mu times d of u. So this is just minus 5 plus mu d of u. That's why we obtain this formula by the definition of the Van-Til conjugate. In the next theorem, we are going to show that f mu defines a class of smooth approximations for the original function f. For any mu greater than 0, the function f mu belongs to C11. That means f mu is a C1 function and its gradient is Lipschitz continuous with Lipschitz constant L given by the following formula. L is norm of A squared over sigma times mu. Here, the matrix norm of A is defined by this formula. It is the supremum of norm of AX where norm x is equal to 1. And we also have this estimate. F mu of x is less than or equal to f of x and is less than or equal to f mu of x plus mu times d for all x in Rn. Note that in the case of simple smoothing presented from the previous lecture, the matrix A is just the identity matrix. And in that case, we can show that the matrix norm of A is equal to 1. So we have a similar result where the constant L is 1 over sigma times mu, and we already proved that in our previous lecture. Now I am going to give the detailed proof of this theorem. As mentioned earlier, the function f mu can be represented as follows. F mu of x is the Fancel conjugate of phi plus mu d of ax for all x in Rn. Okay, so f mu is nothing but just the composition of the Fancel conjugate of phi plus mu d and the matrix A. Okay, now because phi plus mu d is strongly convex with parameter sigma, it is also proper and lower semi-continuous. This follows from the previous lecture because d here is strongly convex with parameter sigma, so mu times d is strongly convex with parameter sigma times mu. If we add a convex function 5, then the new function is strongly convex with this parameter. Okay, so we will see that phi plus mu d star belongs to the class of C11 function. That means this function is C1 and its gradient is Lipschitz continuous with constant 1 over sigma times mu. Okay, from here we will see that f mu is just the composition of a C1 function here and the matrix A. Okay, so its gradient is given by the following formula. The gradient of f mu of x is A transpose of times the gradient of phi plus mu d star of ax. Okay, and so this is true for all x in Rn. So please review the composition formula for the gradient or for the derivative to understand why we have to multiply by the transpose of A over here. Okay, so in the final step we are going to show that f mu is actually belongs to the class of C11 function. To do so, we have to show that its gradient is Lipschitz continuous. Okay, so how come the gradient of f of mu is Lipschitz continuous? We already have this formula for the gradient of f mu. So to show that it's Lipschitz continuous, we just need to apply the definition. Okay, so we're gonna fix any x1 and x2 in Rn, and we are going to estimate the Euclidean norm of the gradient of f mu at x1 minus the gradient of f mu at x2. By the definition, this is it. This is the Euclidean norm of A transpose times the gradient of phi plus mu d star of ax1 minus A transpose times the gradient of phi plus mu d star of ax2. Okay, now for an arbitrary matrix, we always have this formula. Norm of bx is less than or equal to norm of b times norm of x. We can prove this from the definition of the matrix norm. So over here, this is less than the matrix norm of the transpose of A times the Euclidean norm of this. Okay, the gradient of phi plus mu d star of ax1. This is the gradient of phi plus mu d star of ax2. Okay, in the next step, we are going to use the fact that phi plus mu d belongs to the class of C11 1 over sigma mu. That means the gradient of this function is Lipschitz continuous with this Lipschitz constant. Okay, so here we have the gradient of this function of ax1, the gradient of this function of ax2. Okay, so it's less than or equal to 1 over the Lipschitz it's less than or equal to 1 over sigma times mu, that is the Lipschitz constant, times the Euclidean norm of ax1 minus ax2. Okay, now we are going to use this property for the matrix A and see that norm of ax1 minus ax2 is just the norm of ax1 minus x2. So this is less than or equal to norm of A times norm of x1 minus x2. Okay, and then we plug into here and see that the whole thing is less than or equal to the matrix norm of A transpose times 1 over sigma mu times norm of A times norm of x1 minus x2. And now we are going to use another property of the matrix norm, that is norm of a matrix A is always equal to the norm of the transpose of A. Okay, so over here we have norm of the transpose of A, and we also have the norm of A. Therefore, we end up having norm of A squared over sigma times mu times x1 minus x2 here, the norm of x1 minus x2. So finally, we see that the gradient of f mu is Lipschitz continuous with this Lipschitz constant. Now it remains to prove that f mu of x is always less than or equal to f of x, and is less than or equal to f mu of x plus mu d for all x in Rn. The proof goes exactly the same as the proof for the simple smoothing considered in the previous lecture. So please look at my proof in the previous lecture for the way to show that this estimate holds for all x in Rn.